This is Edexcel Further Maths, Further Pure 1 Specimen Paper, question 9. We're given a picture of an ellipse, and it's confirmed for us in the second sentence that we're modeling this thing as an ellipse. The context here is important. You need to read carefully so that you can see exactly what the question is talking about and therefore correctly interpret the questions. The modeling side of this question is part of what makes it a little bit complicated. We have a rectangular garden, ABCD, so the rectangle shown is the boundary of the garden, and then there is an elliptical pond. So this ellipse in the middle shows us the boundary of the pond. Inside the ellipse will be the pond itself, and the line shown, the curve which is the ellipse, is the boundary of the pond, the bank, if you like. The length of the major axis is twice the length of the minor axis. So we know to start with the distance across from left to right for this one is twice the distance up and down. The line AB and the line CD are modeled as the directrices, so we also have this information, that the vertical lines here are not just arbitrary sides of the garden, but they are the directrices of the ellipse. We can link that back to the formula book and remind ourselves of the key results. The directrices of an ellipse are at plus and minus a over e, x equals plus and minus a over e, so vertical lines at those points. And the foci, once we need those, will be in this list as well, along with other useful results and formulae. The ellipse and the rectangle lie in the same horizontal plane. This just means that we're looking at the garden and the pond in 2 dimensions rather than worrying about 3. We're not concerned about whether things are on a slope or if there are other complications going on. We're just modeling this as a 2-dimensional scenario. The first part is to find an equation for the ellipse. To do this, well, we could start with the general equation for an ellipse. X squared over a squared plus y squared over b squared equals 1. Very similar to the equation for a hyperbola, but with a plus instead of a minus. And if you get muddled up, well, A, you've got the formula book. B, an ellipse is just a stretched version of a circle. So think of x squared add y squared equals 1, and then stretch in the x direction by scale factor A, and in the y direction by scale factor B, and now you've got an ellipse. But the A and the B on their own are not enough. We also have additional information. In fact, the most useful thing here is what they've told us about the length of the garden. And at this point, it will be a good idea to start adding information to a diagram. So if we use this 16 over 3 root 3 meters for the total length, that's going to be a helpful thing to incorporate in my diagram. That gives me the distance, for instance, from A to D. But we also have information about the lines AB and CD. We're told that those are the directrices of this ellipse. That's going to be really useful for us because, as I've already mentioned, we've got a formula for the directrices of an ellipse. We know, for instance, that the coordinates here will be a over e, whatever e is, and over here we'll have minus a over e. So we can make a note of that on our diagram as well, and this diagram will gradually be improved as we go along. As we discover more about it, we can add that information to our diagram and keep it constantly updated so that we know what we're dealing with. We were given some additional information which is also going to be useful to do with the height and the width of the ellipse. We can incorporate that in a moment as well. The order in which you do this doesn't make much difference. So we'll start with the fact that a over e minus negative a over e, that's the distance from A to D, that has to be the same as 16 over 3 root 3. So straight away we've got ourselves a useful result. 2a over e equals 16 over 3 root 3. Or if you prefer, a over e equals 8 over 3 root 3. Now, In addition to that, we've got some information that links A and B. We can say that since the major axis is twice the length of the minor axis, we know that A is equal to 2 times B. A, remember, is going to be the coordinate of the point where this ellipse crosses the positive x-axis. We can even include that on our diagram here. So we know for an ellipse of this form, we have A and negative A for the points where it crosses the x-axis. We have B and negative B for the points where it crosses the y-axis. The more you can add to your diagram, the better. The clearer it will be, the more easily you can make use of it to decide the best method to solve the problem, and the more easily you can use it to verify your answers at the end. So if we know that A is equal to 2B, and we also know that A over E is equal to 8/3 root 3, there's only one more thing that we need to incorporate, and that comes from the formula book, where we're told a connection between B, A, and the eccentricity E. Because we've got a link between A and B, we've got a link between A and E, this gives us a third link between those three variables. B squared equals A squared times 1 minus E squared. That's the result we're going to make use of. Now, probably the simplest way, since we're looking for the equation of the ellipse, we don't necessarily need the eccentricity at this point. What we care about is the value of A and the value of B. So let's see if we can find a way of eliminating E. Well, for a start, we've got B squared over A squared equals 1 minus E squared. And this might be the simplest, in fact. B over A, that's just equal to 2. So if A is 2B, let's make sure we don't get this the wrong way around. We can do B over A is equal to a half. There we go. If we divide by 2 and we divide by A, we get B over A equals a half. So over here, we've got a half squared equals 1 minus E squared. This gives us a result for E squared. We know that 1 minus E squared has to be a quarter, so E squared has to be 1 minus a quarter, in other words, 3/4. Since E has to be positive, it's a value between 0 and something, so at least 0. Circle has an eccentricity of 0, an ellipse somewhere between 0 and 1, parabola 1, and hyperbola anything bigger than 1. But this means that E has to be root 3 over 2. Now we've got E, we can use that to find A and B. Might be helpful to have E later in the question anyway, so it's not a huge problem if that's the simplest way through the equations. There are various other approaches you could take as well. I'm going to come back to say that A over E is equal to 8 over 3 root 3. That's now going to give me A times 2 over root 3. That's the reciprocal of E. That's equal to 8 over 3 root 3. If we multiply both sides by E, or by root 3 over 2, we get 8 over 3 root 3 times root 3 over 2. So the 8 and the 2 are going to cancel down to a 4. The root 3 times root 3 gives you 3, and when you divide by 3, that disappears as well. So we should just get A equals 4. And once we've got A equals 4, it's a short step to the value of B. B is equal to a half of A, so we get 2. We can double check by going back to our diagram and adding any information we've now managed to elicit. So for instance, we think A is 4, and we think negative A therefore is minus 4. We reckon that B is equal to 2, and we think that negative B is equal to negative 2. All of that looks sensible on the diagram, and one other quick check you can do is with a calculator, 16 over 3 times root 3, just to see roughly what kind of size number that is. Press the SD button, 9.2 something. So what we're saying here is this is approximately 9.2. That's encouraging because I've already shown here that the distance between the two extremes of the ellipse looks like 8. So getting a value of 9.2 between A and D is consistent with what we've seen. Not only that, but we can verify for ourselves that if we have the value of A, which is 4, and we divide it by what we think is E, root 3 over 2, 4 divided by root 3 over 2 gives us 8 divided by root 3, which simplifies to 8 root 3 over 3, which is exactly what we had written here. If you double that, you're back at 16 root 3 over 3, which is what we had there. So this all fits. It's consistent so far. The only thing we haven't worked out yet are the positions of the foci of the ellipse. But we've worked out the answer for the first part, so we can now write the equation as x squared over 4 squared plus y squared over 2 squared equals 1. And they haven't said what format the equation needs to be in, so I'd be quite content to leave it like that. But if you preferred, you could write it as x squared over 16 plus y squared over 4 equals 1. Or you could even write it as x squared plus 4y squared equals 16, if you want a form that doesn't have any fractions in at all. Next, two water features modelled as particles are to be placed in the pond. The sum of the horizontal distances from the water features to any point on the edge of the pond is constant. So these water features are going to go somewhere inside the area of the pond, somewhere within the ellipse, and the distance from these water features, wherever they happen to be, to any point on the ellipse must be constant, the sum of the distances from the two water features. Now, this may strike you as a hard problem, but it kind of depends on whether you've seen the result before. There is an important result we can make use of here, which is that the distance between any point on the parabola, on any point on the ellipse, and one of the focus points, and the distance to the other focus, if you add them together, you always get a constant. Not only that, the constant you get is going to be equal to 2a. The reason for this, if you look at the ellipse and you pick a point, you can see that the distance to the directrix on the right and the distance to the directrix on the left, if you add those two together, then of course you're always going to get the same thing, because no matter where you are on the ellipse, distance you travel if you move to the right and the distance you travel if you move to the left. Got my port and starboard colours mixed up here. But those two distances have to add up to 2 times a over e, simply because of the position of the directrices. Now, if we use the fact that the eccentricity is the ratio between the distance to the foci and the distance to the directrices, then we immediately get this result. So we can say that this result happens because PD plus PD dash equals 2a over e, and PS equals EPD, PS dash equals EPD dash. So PS plus PS dash is equal to E times PD plus PD dash, which of course is E times 2a over E, which is just 2a. So it turns out 2a, which is the length of the major axis from the point A to the point minus A, that distance is always the same as the sum of the two distances if we travel from any point on the ellipse to the first focus and from any point from that same point to the other focus. If you add those two numbers, you'll get the same result as if you go directly from the point minus A to the point A. This may seem a bit strange. In fact, what I've drawn isn't quite right, because clearly the distance we've got here is not the same as between A and minus A. What we need is the distance between the focal points. Crucially, these points are not the same as the very end points. We want this point here and this point here. This doesn't seem quite so strange anymore. These points are the focal points, and the formula book has some helpful hints for us here. The focal points for an ellipse are at plus and minus AE0. So they're closely related to the value for the eccentricity. They're similar to what we've got for the directrix, but we're multiplying by E instead of dividing by E. So we have AE for this point, and we have minus AE for this point. Since we've got the values of A and E, recognizing that this is the property is how we're going to pick up the first of these 2 marks, and then applying the property is how we get the last of the 2 marks. So all we need to do here is say that A equals 4 and E equals root 3 over 2. From there we can find the position of the foci, plus and minus AE0. That's equivalent to plus and minus 2 3 0. And that's our answer. That's where you're going to need to put your water features. Just one point about the wording here. They said that the sum of the horizontal distances from the water features to any point on the edge of the pond is constant. When I first read that, I was imagining a horizontal line from a point inside the pond. But in fact, what they're saying is essentially a flat line. We're not moving up into the 3rd dimension height. We're staying within the 2-dimensional model of the garden and the pond. So although the water feature may stick up above the pond, we're not measuring the distance from the top of whatever crazy fountain they've put in. We're measuring the distance directly from the position essentially flush with the pond. Now, the last part of the question is worth 5 marks, so it's likely to take a bit more work, or at least require a bit more clever thinking. Gnomes, modelled as particles, are to be placed on the edge of the pond. Each gnome will be exactly 2 meters from a water feature. Find all the possible coordinates for the gnomes. They're to be placed on the edge of the pond. In other words, these are points which are on the ellipse. Each gnome is exactly 2 meters from a water feature. In other words, we need points that are a fixed distance from the foci that I found the positions of in part C. What we're going to find helpful here is a diagram. Here's one I made earlier. This diagram is basically, I know it's a prettier diagram than you might produce for yourselves, but it doesn't need to be massively accurate. It just needs to show us enough of the situation that we can make sense of a valid method for solving. Now, there are a couple of different approaches you can use here. We know, for instance, on this diagram, we've got some important information. We can use the fact that there's a directrix that we know about, and the focus, the distance to the focus, is also something that we know. So if we take a line from the focus to here, that distance is 2. We're told that already in the question. Now if we consider the directrix, which is going to be at some further point, this is the 8 root 3 over something. This line is somewhere like, let's see, it's about 4.6, I believe. So I'm going to draw it here. I'm doing half of 16 root 3 over 3. So half of 9.2 is about 4.6. We're down here. The distance to that directrix horizontally is actually directly related to the 2 that we've got here. Because remember, the definition of the eccentricity is simply the ratio between the distance to the focus and the distance to the corresponding directrix. So we can use that idea here. That's going to come in quite handy. It's not the only approach. You might already be thinking, well, hang on, I've got a circle here. I can use a circle equation. And yes, you absolutely can. It's the method I used when I first did this question the other day. It works just fine. But here's what happens if we try the directrix approach. The distance to the focus divided by the distance to the directrix is always equal to E, which in this case means that the distance to the focus, which is 2, divided by the distance to the directrix, which we don't yet know, is equal to E the eccentricity, which we calculated earlier as √3/2. Once we've got that, it's easy enough to find PD. Why do we want PD? 4/√3. Well, the reason is we can use that to give us the y coordinate, because this is the x coordinate, or almost the x coordinate. This is how far we need to move from this point to this point. If we use the fact that the directrix has x coordinate of a/e, in other words, of 8/3/3, that means that the x coordinate of my point must be 8√3/3 minus what we've just calculated here, 4√3/3, which of course is 4√3/3. We can check on our diagram, does it look like it's perhaps halfway between the origin and here? Well, maybe not on my diagram so much, but not far off. In fact, if you look carefully enough, you'll probably find, give or take the precision of my directrix, it's not far off at all. So coming out as 4√3/3 for this distance, which is exactly half the distance from the y-axis to the directrix, seems close enough, especially for an approximate diagram for my directrix. So that's given us the x coordinate, and to find the y coordinate, all we need to do is substitute into the equation for the ellipse, because remember, these gnomes are on the ellipse, they're on the edge of the pond. We have x squared over 4 squared plus y squared over 2 squared equals 1. So x squared, we can simply square 4√3/3. That'll give us 16 times 3/9. In other words, 16/3. And if in doubt, use the calculator. We're dividing by 4 squared. So that's going to sort out the 16 for us quite nicely. We're adding y squared over 2 squared, so y squared over 4. So a third plus y squared over 4 equals 1. Y squared will be 2/3 times 4. So we've got 8/3, and that gives values for y of plus and minus the square root of 8/3, which your calculator will probably simplify most easily for you. So let's head across to there and get the square root of 8/3, 2√6/3. Now remember, there are two of them, plus and minus 2√6/3, but in fact even that doesn't tell the whole story, because if you look back at our diagram that we've got here on the left, we can immediately see there are 4 different places where the circle of radius 2 crosses the original ellipse. These are the places that are exactly 2 meters from one of the 2 water features. So we've found the coordinates of one of them. In fact, with this plus and minus y, we've actually found the coordinates of 2 of them, because there's a corresponding point down here that's also the same distance from the directrix. But we've also found the coordinates of the other 2 because we've got symmetry involved. And that's all we need to say here, by symmetry, and there's only one final mark for this last step, so it doesn't pay you to go through and do the entire process any more times. You might as well just recognize that the other points will have the exact negative x coordinate and the same y coordinates as these 2. So we're going to have the points plus or minus 4√3/3 and plus or minus 2√6/2. Our first point looks like this. Our second point looks like this, with a negative in front of the y coordinate. Our third point has a negative in front of the x coordinate instead. And then we have one where both the x and the y coordinates are negative. So you can double check your diagram that these are sensible. 2 root 6 over 2, for instance. We can check the size of that number is about 1.6-ish. So what we're saying is we're expecting a y-coordinate of about 1.6, which at least is consistent with an ellipse that doesn't go any higher than 2. We either have an x-coordinate of 2 point something and a y-coordinate of 1.6, or an x-coordinate of minus 2 point something and a y-coordinate of 1.6, or minus minus, or plus minus. These are the 4 points that we're looking at.